So last time we learned about pH, the pH scale, and the relationship between hydronium ion concentration and the pH. And we looked at strong acids. Today we're going to look at weak acids as well. So when we look at finding the pH of an acid solution, we need to realize that there's two possible sources of those hydronium ions. One is the ionization of the acid itself. This is the more obvious one. But then there's also the autoionization of water. So most of the time we can ignore the autoionization of water because it is so small compared to the acid that's been added to the solution. But if we have a really dilute acid solution, then it does become significant. So we can't always ignore that. So strong acids, by definition, ionize completely. And so they are pretty straightforward. The concentration of hydronium ion is equal to the concentration of the strong acid. So the example here, 0.1 molar HCl, this is a strong acid. All of it ionizes, and so we're going to have 0.1 molar hydronium ion concentration, and the pH will be 1. No ice tables needed. For weak acids, we need to use an ice table and calculate the hydronium ion concentration using equilibrium constants because they only partially ionize. So here's an example ice table. So we know the initial concentrations. The initial concentration of the acid is whatever the concentration is stated as. The initial concentration of hydronium, we say, is approximately 0, because it's not actually 0. It's 10 to the minus 7, but most of the time we can ignore that. And the concentration of the conjugate base is also 0. Then we put in the changes, and then we add those two rows together, and we get the equilibrium expressions. We stick that in to the Ka, and we can calculate what X is. So let's do an actual example here. Find the hydronium ion concentration of a 0.250 molar hydrofluoric acid solution. So this is going to require an ice table. So I'm going to write the formula or the equation here. And I'm just going to kind of do it more shorthand. Do we really have to have the state symbols here? No. Do we have to write H3O plus and H2O over there? No. We can understand that we mean H3O plus here. If you want to write the whole thing out, that's fine as well. So we make our rows and our columns. And it would be much faster if I had all of this typed in here, and I can bring it up with animations and just fill things in. The reason I don't do that is because if I have that done, then I go too fast, right? And you guys don't have enough time to write stuff down. So if I have to write it down, then I know that you have enough time to write it down. So that's why I'm doing this. Okay, so we drew the ice table. We put in the initial concentrations. So this is the initial concentration of the acid solution, 0.250. So we write that in here. And what do we write for the hydrogen ion concentration? 0. So I'm a scientist. I pay attention to details, and so I cannot bring myself to say that it is 0, so I always say approximately 0. If you don't put the approximate symbol there, that's fine, but I'm compelled somehow. And fluoride ion concentration, also 0, right? So now we look at the changes. Both sides here are 0, or both concentrations are 0. So the only direction this equilibrium can go is to the right. So we're going to gain x for H plus, and we're going to gain x for F minus, and HF is going to lose x. Most of these are going to end up with coefficients of 1 for the weak acids, and so there's nothing tricky here. Then we're going to add the top two rows to get the bottom row. 0.250 minus x, x, and x. Ka for this acid is going to equal the hydrogen ion concentration times the fluoride ion concentration divided by the HF concentration. So we take the concentrations of the products divided by the concentrations of the reactants. So all of this should sound very, very familiar because we did this last week. Okay, so now what we're going to do, we're given the Ka, and we have these equilibrium concentrations in terms of x, so we're going to plug them all in. We're going to get 3.5 times 10 to the minus 4 is equal to, and the numerator is going to be x times x, so I'm just going to write x squared. And then we'll divide that by 0.250 minus x. And now we need to find x. There's two ways we can find x. We can use the solver. Using the solver is always correct, right? And once you learn how to use the solver, I think it involves less thinking about the problem than using the x is small approximation. My personal preference is to avoid things that involve a lot of thinking, because when I think about stuff, sometimes I get it wrong, right? So if things are really straightforward, that's better. So go ahead and plug that into the solver. I'm going to do the x is small approximation. So the x is small approximation says, well, this x is so small compared to what I'm subtracting it from that it doesn't matter. So the analogy was the truck full of peaches at the weigh station, and it drives away and one peach falls off, and nobody cares because it's so small compared to the weight of the truck. So essentially then we can ignore that x. So then we end up with x squared is equal to 3.5 times 10 to the minus 4 times 0.250, and if we do the square root of both sides, then we get x. So let me do that. And I get 0.009354. And I'm just kind of writing down 4 sig figs because I'm pretty sure that's more than I need.
I forget when we can solve the x. Is it when the Ka is so?
Good question. When can we do the x is small approximation? If Ka is small, here it's small, but it's kind of questionable in my mind. So K needs to be small, and then the concentration that we're subtracting x from needs to be relatively large. So 0.25 is relatively large. 0.0025 would be small. Okay? So if you like x is small, you can always try that, and then we have to check and see if it is appropriate. And the way we check is we take our x that we got, and we divide it by the thing we subtracted it from. And we want to see if this is 5% or less. And it's 3.7%. So we could use X is small. So those of you that did it on the solver, what did you get for X? 009 what? 18. Is there another digit? 07. Okay, so I'm going to round that up to a 1. So those are pretty close. Which one do you think is better or more accurate? The solver, right? So, there are very few things in chemistry, general chemistry, that change. Like, what are the big updates in your field? Well, they named it some new elements a few years ago. Then that's about it, right? General chemistry doesn't change. But this is one of the things where how we teach general chemistry is in the process of changing. Because when these books were written, you could not assume that people had a calculator that could solve quadratic equations, right? And so we taught the X is small approximation. Some instructors actually insisted that you use the quadratic equation to solve the other ones. Oh my goodness. Now I think the X is small approximation, I don't know that, in the near future, I'm not sure if I'll even teach that anymore because we don't really need it, right? But it's in the book, so I'm going to teach it to you. If you don't want to learn the X is small approximation, you're fine. You're absolutely fine. So either of these answers should be okay. I would go with this one. Well, actually, we would have to round that, wouldn't we? 0.0092 is probably the better answer there. Well, let's see what the answer is. 9.4. So the book used the X is small approximation and got 9.4 here. We got 9.2. Small difference, not a big deal. Any questions about that one? So we did ice tables in chapter 16. As you can see, we have ice tables in chapter 17. We're also going to have ice tables in chapter 18. Okay? So if you like ice tables, that's great news. If you don't like ice table, that's terrible news. But I tell you that because if you haven't gotten them down yet, you need to, okay? And the way you figure them out if they're not making sense is you ask me a lot of questions, okay? That's probably not best done during lecture, but during lab we have time. And I will literally stand there all day and answer your questions because I want you to get it. When you get it, then your eyes light up. And that's a rush. I mean, that's like just a teacher's high when the student is like, oh, I see. And you're like, yes. So I would love it if you give me some of those moments, right? Anyway, going on. This is a similar problem, but they're asking us to find the pH of a weak acid solution. Well, what do we need for pH? The concentration of the hydronium ion. So we're going to do the same process, but then we're going to take the hydronium ion concentration and calculate the pH from it. So acetic acid, right? We should know the formula for that. Do we need the formula to do the problem, though? Absolutely not. All of the weak acids that we'll be dealing with are, monoprotic. And so here, we really don't need the formula at all. And so a common thing is to just call it HA, where A kind of stands for acid, right? It doesn't stand for acetate, but acid. And then what happens to the acid is it loses its proton, and then we get its conjugate base. So this equation applies to most weak acids, and it's less writing because we don't have to do the HC2, H3O2 thing. If you want to write the the complete formula, no problem. Ice table. ICE. So where do I put the 0.0150? That's the initial concentration for the HA. And then what we are interested in knowing is, well, how much of that ionizes? Initial concentration for H plus, 0. And for A minus, 0. So then we've got changes. The HA is going to lose some amount, X, and H plus is going to gain it, and A minus is going to gain it, 0.0150 minus X, X, and X. So far, this is the same as the previous problem. The only thing different is this number. So there's very definitely a pattern happening here. So Ka is H plus times A minus over HA. Then we're given what Ka is. In an exam problem, you'll be given the Ka. Homework problems, they might not tell you what it is because you have access to the textbook, and so you're supposed to go look it up. So I've got these guys down here, X times X, I'll call that X squared. And I've got 0.0150 minus X. So we can solve this one of two ways. Go ahead and do the solver business. And I am going to do the X's small, just to see what happens. Because actually I know what happens. So that's what I get for the X's small. And then I need to check it. Oops, I lost a 0. – 3.5%. Could we use that answer? Sure we could. So if we use that answer, then the pH is the negative log of that concentration. .2843, 3.28. Let's compare that to using the solver. What value did you get for the solver? 5106. Yeah. So this one's even closer, right? So we could calculate the pH for that one. 0.0005106. 3.2919, 3.29. Is this x's small value acceptable? Is it good enough compared to using the solver? Sure. It differs in the last significant figure. And remember that in PHs, the numbers before the decimal point are not counted as significant figures because they are holding the decimal place. This 3 is because there's 3 zeros in front of the 5. Any questions? Okay.
It is not about this one. It is just about the weak acid and the strong acid.
Mm-hmm.
So we learned last semester that strong acid does not dissociate, or we cannot like have it split as H and as.
We do split up the strong acid. The weak acid doesn't split up very much. So like when we're writing net ionic equations, that's when we talked about strong acid, weak acid in Chem 1A. So in a net ionic equation, if it's a strong acid, you separate it into ions. If it's a weak acid, you write it as the molecule. Okay, did you have that backwards in your head?
Yeah.
Yeah. That's okay. Yes?
Can you explain about the sig figs?
Yeah, I can explain about the sig figs. So a logarithm is finding the power of 10 that a number is. So if I find the log of 10 to the 3, that's going to give me 3. The log of 10 to the minus 5 is equal minus 5. So the number before the decimal point is the power of 10. Okay, so, I mean, because we could also write this as 1 times 10 to the minus 5, right? If I have the log of 5.106 times 10 to the, so this one is 10 to the negative 4. I'm going to do 10 to the negative 7. Negative logs of the pH there. You can do the math. That's going to come up to be 6.29. And I'm not doing that because I can do logarithms in my head. I cannot. I'm doing it because I just saw this one. This is 5.106 times 10 to the negative 4, right? So the 4, one less is the 3, and then these digits. So over here, if it's the same number times 10 to the minus 7, then I know that the number before the decimal is 1 less, or 6, and the stuff after the decimal point is the same. So the number before the decimal point is related to the power of 10. The power of 10 is not a significant figure. Those would be decimal holding zeros, right? The sig figs are the number before. And so here, if this had 2 sig figs, then I round this to 2 decimal places. Okay? Yeah. Once you see it, it makes sense. If you never see that part, you're fine. That's not going to be a big deal. But, you know, if you're confused, like, it seems like she's, like, doing weird things with sig figs. I'm actually not. It's what you're supposed to be doing. Like I said, in this class, we're not going to bang you over the head with sig figs, right? The idea is that you write down a reasonable number. Write some extras down until you finish your calculations, and then round it off. Well, what if you really hate sig figs? Well, you know, always keep 4 or 5 digits, non-zero digits, and then at the end round it to 2 or 3. And most of the time you'll be absolutely fine, right? Any other questions? Finding the pH of a weak acid solution when X is small doesn't work. So, guess what? This one we can't use X is small. So here we've got 0.010 molar. So now this starting concentration is smaller. The previous example was 0.25, and now it's 0.01. So this is a smaller concentration, and Ka is still smallish, right? So we're going to write the ice table the same. So I can write this instead of HNO2, I can call it HA. If you want to write HNO2, that's absolutely fine. Okay, I, C, E. We're going to fill in the initial row. The concentration of the acid is given, 0.010. We're assuming that the hydrogen ion concentration is approximately 0, because it's super, super small. And the A minus, which here would be the nitrite ion, is going to be 0. So then this is minus X and plus X. 0.010 minus X, X and X. So far we've got 3 examples that are pretty much the same. We're going to spice it up here very soon. So there's my Ka value, and I take my equilibrium row, and I've got X squared divided by 0.010 minus X. You could try X is small, but when they say it doesn't work, why bother, right? So this one, you either have to use a quadratic equation or a number solver. So let's use the number solver. So 4.6 times 10 to the minus 4 on the left of the equals, and we type this in just like it looks on the right side, and we hit enter, and we press 0 to tell it, let's just start with X is 0, and enter, enter, and it tells me 0.001927. Anybody need help with their solver? Were you able to get this number out of it? Yeah, awesome. Okay, so here we're asked for pH, right? So X is equal to the equilibrium concentration of hydrogen ion. So negative log of this number. There's 2 zeros. This would be 10 to the minus 3. There's 2 zeros. This pH is going to be 2 point something. .7151. And if we're keeping 2 significant figures, which is suggested by our Ka, What should we round this to? 2.72. Yeah. Because it's the decimal places that are the significant figures. This 2 is just locating the decimal point in the number. Any questions? Okay, so let's mix it up a little bit. So we've got a weak acid solution here. They're telling us what the pH is, and they're asking us to find Ka. So this is kind of backwards of the previous 3 problems, where they gave us Ka and wanted things like pH. We're going to approach it in very much the same way. We're going to write a chemical equation for the ionization of the acid and make an ice table. Here, we don't know what the weak acid is. They didn't tell us the weak acid because if they did, we could just go look up the constant, right? So how do we write the formula for this? Well, this is where that generic HA comes in very handy. It's also really useful when you have some of these weak acids with really, really big formulas, and we don't even need them, so why write them down? So we're going to do our ice table. ICE. So this 0.175 is our initial concentration for the weak acid. So I'm going to put that in here, 0.175. What's the initial concentration for H plus? 0. And for A minus? Also 0. Now, we could do all the X's, but that's not really going to help us. So this is like the calculations you did for last week's lab, right? Where we used the spectrophotometers and we measured the absorbance of the solution, and we could calculate the concentration of the complex ion, and then we used that to find the equilibrium constant. This is the same idea, but instead of an absorbance, we've been given a pH. From the pH, we can find the hydrogen ion concentration. So the hydrogen ion concentration is equal to 10 raised to the power of negative pH. So 10 to the negative 3.25. 10 to the negative 3.25. Domain error. What did I do wrong? Oh, I did log. Yeah, I just can't do log of a negative number. 10 to the x, there we go, minus 3.25. 0.25. Okay. So it's giving me 0.0005623. It was 3.25, it's got 3 zeros. So this is the equilibrium concentration of the hydrogen ion. We can measure that with a pH probe. So here we know that this is 0.0005623. So by comparing the initial and the equilibrium value here, we can figure out how that changed. Well, it had to increase by that amount, right? 0.0005623. Well, if this increased by that amount, how much did A minus increase by? the same. And 0 plus that number is the same. How much did HA decrease by? This number, right? So then down here, this isn't going to fit very well. We have a 0.175 minus 0.0005623. Well, let's do the math there. 0.175 minus 0.0005623. So that is equal to 0.1744. So this is kind of all together. The box wasn't big enough. So we're still going to use Ka expression. But now, instead of plugging something in for Ka, we're solving for Ka. So Ka is equal to these numbers in there. Well, H plus and A minus are the same number, so we can just write that as the number squared. And that's going to be divided by the 0.1744 that we calculated for the HA equilibrium concentration. Oops, I forgot the squared. So 0.0005623 squared divided by 0.1744. So normally I have my calculator in normal or decimal notation, and the number that just popped up has more than 3 zeros, and I don't want to get my finger out and count. So I am going to change the mode on my calculator to scientific notation so that I don't have to do that. 1.039. I'm going to stick that one in there because I don't want to roll up all the rounding. Times 10 to the minus 5. Were you able to get that on your calculator? So that would be 1.04 times 10 to the minus 5. You got 1.8? Okay. I did something wrong. Thank you for telling me. Yesterday I did a whole problem, and then they told me that I had an extra 0 over here. It's like, well, guys, that would have been nice to know right away. So let me try this again. Actually, I'm really curious what I did wrong. Oh, I don't know what I did, but 0.0005623 squared divided by 0.1744. Yeah. One 1.9 rounds to 1.8 minus 6. And yeah, Ka doesn't have any units. Still bugs me. What did I do wrong? Yesterday I forgot to square the numerator, so that was a problem. Any questions? So the initial concentration and Ka of several weak acid solutions are listed. For which solution is the X's small approximation least likely to work in finding the pH? Yeah, it's going to be C. So how do we figure this out? Well, if we want X is small to work, then we want a small Ka and a large concentration. That is when it's most likely to work. So for least likely to work, we're looking for the opposite. We're looking for a large Ka. So both C and D have larger Kas than A and B. And we're looking for an initial concentration that is smaller rather than larger. Any questions? I don't anticipate putting a question like that on the exam. I just don't really see the point. Okay, which of these solutions is the most acidic? Meaning it's got the lowest pH. Well, first thing to think about is, well, what's different between the choices? Here we have the same concentration, and this one has a different concentration. Is there another difference? Yeah, we've got this one's a strong acid, and this is a weak acid. This is the same one here. So we have a 0.1 molar strong acid or a 0.2 molar weak acid. It's going to be the strong acid. The strong acid ionizes completely. The weak acid ionizes partially. And you might say, well, yeah, but if it's 50%, then they'd be the same, right? Well, what we're going to see is that weak acids ionize much less than 50%. It's more like 5%. It's like super small. So that's our answer for the lowest pH.
So we look for the element, not for the concentration.
Well, we're considering the concentration, but we also have to consider strong acid, weak acid. So this one's strong. Now, if this was like 50 molar HF, then that might be more acidic, but almost always the strong acid's going to win. So I mentioned what percent ionizes. So we can talk about the percent ionization of a weak acid, and this is going to be the amount of hydronium ion present at equilibrium, which represents the amount that actually got ionized, divided by the initial concentration, which was the whole amount, times 100. And again, for percents, the general idea for a percent is it's the part divided by the whole times 100. So if you remember that, a lot of times you can figure out what the equation is even if you don't really remember it. So what part am I interested in? Well, I'm interested in how much got ionized. Well, how would I measure that? Well, I need the concentration of the part that's ionized, right? And I'm going to divide it by the whole thing, which is how much acid we started out with. The percent ionization is relatively small for weak acids. Let's calculate that. Find the percent ionization of a 0.25 molar acetic acid solution at 25 degrees Celsius. Ka is 1.8 times 10 to the minus 5. So I don't feel like writing all those letters, so I'm just going to nickname it HA. HA ionizes to make H plus and A minus. So here, the percent ionization is going to equal the H plus concentration at equilibrium divided by the HA concentration initially times 100. Do we know right off the bat what the H plus concentration is? No, we don't. Do we know HA? Yeah, we do. So we have to find the hydrogen ion concentration. Okay, this is just like those first three problems. Draw an ice table. Whoops. I don't know what happened to that line. I, C, E. So here's my initial concentration, 0.250, and the other initial concentrations are 0. And then minus x plus x plus x, 0.250 minus x, x, and x. So 1.8 times 10 to the minus 5 is equal to x squared over 0.250 minus x. It would be interesting to see what you can do faster. The x is small approximation or the solver. So here's just a little shortcut. If you use the solver on a previous problem, you may only have to change this, a couple of digits on this number and that number, and the rest of it's going to be fine. So using the solver, I get that x is 0.002112. Anybody else get that? And we're either correct or we both made the same mistake, right? Yeah. Okay. We found the hydrogen ion concentration. Right? That equals H plus. We're going to get to some where what we end up with down here is not just X. And it might be something like this. And so, we do have to be a little careful. We can't just assume that X is always the hydrogen ion concentration. So percent ionization is going to be 0.002112 divided by 0.250 times 100. Zero 0.8448, 0.84%. That's really small, right? When we say weak acid, I mean weak acid, right? Only a little teeny tiny bit ionizes. But it's an equilibrium, right? And so if something pulls one or the other of these away and causes those to decrease, there's a whole bunch more acid here that will continue to ionize. And so it's always going to keep this relationship, but the percent ionization is going to be small if it's just by itself. Any questions? Yeah.
How can we like put the elements in the rest table as H8 and H plus A? How does that work?
Okay. So what I'm doing there, let's see, use a color I haven't used yet. Oh, maybe orange. So HC2H3O2 is our acid, right? And so we're going to call the C2H3O2 we're going to call that A minus, and this part we're going to call HA. So the A stands for that whole mess. Because the only thing we care about is this hydrogen that's coming off, right? So we can write out the whole formula. There's no problem with that. If we don't know what it is, then we kind of have to use HA. But this is less writing than doing this. And so that's why I do it. Does that make sense? Yeah. Any other questions? 0.85%. I got 0.84. It's because they used the X as small approximation because they're, I don't know, they are what they are. Okay, so the equilibrium hydronium ion concentration of a weak acid will increase as the initial concentration increases. But the percent ionization actually decreases. And here we have an example for nitrous acid. 0.2 molar has a 4.8% ionization, but at a 2.5 molar, it has 1.4%. And that kind of seems wrong, doesn't it? They should be the same, or it should go the other way. Well, why is it that way? Well, here's our generic equation, right? So, and so that gets translated into x squared over HA minus X. So these are equilibrium. This would be the initial. You know, that's not really helpful at all. Well, maybe it is. This is a thing that is hard to explain. So the percent ionization is the H plus concentration at equilibrium divided by HA initial. If I double this concentration, does that mean that this X gets doubled? No, it doesn't, because this is a square and this isn't squared. It's not a linear relationship. So if you double HA, that does not mean that you're going to double H plus. So then the percent ionization is going to change. I don't think this is the best way to explain that, but it's better than yesterday when I completely blanked. Which weak acid solution has the greatest percent ionization? The smallest. Yeah. The smallest concentration has the greatest ionization. Is this something you need a real firm grasp on? No. Actually, it isn't. This is a minor point. If you understand it, if you can reason it out, that's great. If you completely ignore it, I'm not talking about calculating percent ionization, but I'm talking about predicting relative to the concentration, does it go up or down? That's not at all important in my mind. Okay, so what if we have a mixture of acids? This could get complicated. So if we have a weak acid and a strong acid, we can focus on the strong acid and ignore the weak acid. So if we have 0.1 molar HCl and 0.10 molar HCHO2, that's formic acid if you care, we have 3 sources of hydronium ions because now we have 2 acids plus water itself. So here's our strong acid, here's our weak acid, and there's water itself. Here are the Ka values. We don't give a Ka value here because it's essentially infinity. This goes to completion. So this is a single arrow, and these are the equilibrium arrows. So we're going to get a lot of H3O plus from the HCl, right? If it started out at 0.1 molar, then it's going to produce 0.1 molar H3O plus. So when we go to make the ice table for the weak acid, the initial concentration of hydronium is not 0 anymore because of the strong acid. So the strong acid produces all this hydronium ion. That is now our starting point. So when we do the ice table, things are going to come out a little bit differently. We're going to end up with X here being 1.8 times 10 to the minus 4. And when we try to calculate the hydronium ion concentration at equilibrium, we add that to this. It doesn't matter because X is so small. So if you have a strong acid and a weak acid, you can ignore the weak acid. What if we have 2 weak acids? Well, there's still 3 sources of H3O plus. Sometimes we can ignore the weaker weak acid. And this will happen when the Kas for those acids are very different. Like they differ by a factor of several hundred. Like 200 times or 500 times or 1,000 times. Not just twice as big. Right? So if the Kas are very different and the concentrations are similar, or the stronger acid is higher in concentration, then we can ignore the weaker acid. Okay, so let's look at this one. Find the ClO minus concentration of a mixture that is 0.300 molar HF and 0.100 molar HClO. So look at these equilibrium constants here, the Kas. These differ by a factor of 10,000, 10 to the 4, right? So those are really different. And these concentrations are similar. So if we were calculating the pH of this solution or the hydrogen ion concentration, we could just focus on the stronger acid and get our answer. But that's not what they're asking us for. They're asking us for the concentration of ClO minus, which is the conjugate base of the weaker weak acid. So here, when I have 2 different acids, I'm not going to use the HA thing because that could get confusing. So we have 2 weak acids, we're going to have to do 2 ice tables. So we start with the strong one. So we have HF goes to H plus F minus. You guys tired of drawing lines? I'm getting tired of drawing lines. So I'm going to show you. You can actually do this if you're neat about it. You can do this without drawing a whole bunch of lines. So I've just got my invisible. I've got a table with invisible lines, right? Sure, we do. Initial concentration of our weak acid. That's the 0.1 molar. Oops, sorry, it's the 0.3. You got to remember which one we're talking about. 0.3. And here, the hydrogen ion concentration is going to start at 0. With the first ice table, you do start at 0. We look at the stronger acid first because it contributes the most. And this will be 0.
So HF is the stronger?
HF is the strongest because its Ka is larger than HClO. So then my changes in terms of x's, and so I've got 0.300 minus x, I have x, and I have x. And so my equilibrium constant for that is 6.9 times 10 to the minus 4, and that's going to equal my products times each other, so that gives me x squared divided by 0.300 minus x. X equals 0.01405. Just to keep those from running into each other. That is equal to the hydrogen ion concentration produced by the stronger acid. Did somebody else get that number?
Yes.
Yes, thank you. Okay, so now we take the weaker acid, the weak acid, and that is HClO. That is in equilibrium with H plus and ClO minus. Let's do this one in red, just for fun. So ICE. Initial concentration of the acid is the concentration given in the problem, 0.100. But this is where things get different. Is the hydrogen ion concentration 0? No. It's this number that we just calculated. This is going to affect this equilibrium. So I put that number I calculated in here, 0.01405. What's the initial concentration of ClO minus? 0. Because you could think of this kind of sequentially. You've got this solution, you put in the HF. It does its thing, right? Makes hydrogen ions. And then I'm going to take the weaker acid, the HClO, and put that in there. So what it's seeing is not just plain water, it's seeing a solution that already has this much hydronium ion in it. Okay? So we're always going to look at the stronger acid first, and if you want to think of adding them one after the other, that's fine. Okay, so this is going to go down by x, up by x, and up by x. So 0.100 minus x, 0.01405 plus x, and x. So for this one, my equilibrium constant, my Ka, is 2.9 times 10 to the minus 8. And so these are the products. So I've got the quantity 0.01405 plus x times x divided by 0.100 minus x. I'm just going to use my solver again. This time it's a little different. I've got 0.01405 minus x, plus in parentheses, times x. And then I'm dividing by 0.1 minus x. And this is giving me a whole bunch of zeros.
Yep.
So what I'm going to do is I'm going to get out of that, and I'm just going to press that variable button X and enter, and it's going to pull that value I just found with the solver back up, and it's going to show it to me in scientific notation. If you want me to show you how that works later, I'd be happy to. I only discovered that this year. I've just been typing things in. So here my X represents the ClO minus concentration at equilibrium. What if I was calculating the pH or the hydrogen ion concentration? I would be taking this number that I got from that ice table, and I'd be adding this teeny, teeny, tiny number, which is not big enough to matter, right? So does this one affect the H plus concentration? No, it doesn't. So if we were just doing H plus, we could just do the first ice table and stop. Any questions?
So if we want the pH, we'll just do for the stronger acid, we'll get from it.
Right. If they're saying, what's the pH? We could stop here. Let's find out what the pH is. So negative log of 0.01405, it's going to be 1 something. .8523. Over here, what's the hydrogen ion concentration? Well, it's that number, right? 0.01405 plus 2.064 times 10 to the minus 7. Well, that's still 0.01405. Because this is a little tiny amount. So, because this is relative to that, we're adding or subtracting relative to a larger number, it's not significant for this. This X, though, is significant. Because here, you're comparing it to 0. So this is more like you've got a child with a play, a rather large, but it's a toy semi-truck, right? And they put like 10 peaches in it, and they weigh it on their pretend scale or the bathroom scale. And they drive away, and 1 peach falls off. Does that make a difference? Yeah, it probably will. So here, X isn't 0, it's just really, really small. Any questions? Yeah.
So to find the hydrogen concentration of a weaker base, you have to start with the stronger one and then plug that in for hydrogen?
Yeah, so if you're calculating anything for the weaker acid, you have to find the hydrogen ion concentration for the stronger one. because that, excuse me, that will be your initial concentration here. Because if we think about this equilibrium, let's think about putting the weaker acid in first and then adding the stronger one. So we put the weaker acid in first and it sets up an equilibrium. Then we put the stronger acid in and it adds a bunch of this H+. What does that do to this equilibrium? Does it shift to the right or to the left? It's going to shift to the left, right? So the presence of the hydronium ion from the other acid causes this to ionize less. It suppresses it. Okay, good question. Anybody else? Yeah.
So, but the pH for the, it is the same, right? For the
It would be
whole
the same.
reaction,
Mhm.
basically. Okay.
Yeah. Because if we take these two numbers and add them together, we get that same number.
Yeah, right.
Yeah, so the pH will be the same. It doesn't contribute enough hydrogen ions to affect the concentration. So, this is like maybe somebody coming up and throwing a peach onto the truck. Well, yeah, there's an extra peach on there. Does it matter? No, because it's so small. Judging relative pH. Which solution is most acidic? One that's 1 molar HCl, 2 molar HF, or 1 molar HF and 1 molar HClO? First of all, which are strong acids, which are weak acids? This is a strong acid. Everybody else is a weak acid. So how much do weak acids ionize? Not much. I just didn't hear the word not. You said it right. Not much. So, we're talking 5, 10% maybe, really small. So here, the total acid concentration is 2 molar, but these are weak acids. Here, the total acid concentration is 2 molar, but it is also a weak acid. Can I compare these two? Not without knowing their Kas. I'm going to guess that they're fairly similar. But this one is going to ionize completely, and so we're going to get 1 molar hydrogen ions. From this one, I'm going to get a fraction of 2 molar. So the most acidic will be the one with the strong acid. Okay?